Welcome to this installment of rotational momentum, or better known as, more accurately known as, angular momentum. Where we're situated here in our study of circular and rotational motion is we have our comparison, our comparable formulas, relationships, linear momentum, and angular momentum. We've previously discussed the effects of mass and inertia and the moment of inertia and how they're different from each other. So in this installment, we are going to look particularly at momentum and change in momentum, angular momentum and change in angular momentum. That's our focus for today. So let's begin just a review of our linear momentum formula and its units. It is kilogram meters per second. Of course, this is the velocity. And this is the mass. And our dear friend, momentum. So it is expressed in units of kilogram meters per second. Now, angular momentum is the product of the moment of inertia, which we know is proportional to mr squared, more sensitive to the distance than to the mass. And the r we should think of when evaluating shapes as what is the average distance of a molecule to the rotational axis. And if the r is larger, then it has a greater moment of inertia. And if it is smaller, it has a smaller moment of inertia. And that's why we see things like a hoop versus a ball. The ball will have less moment of inertia, will take less time to get down an inclined plane than a ring or a hoop would. So that's the moment of inertia, I. And that is a comparable term to the mass. And we have a linear velocity. And of course, then the omega is, and I'll write that out, omega is the angular velocity. And of course, we previously learned that omega is equal to 2 pi over t. And if it's a constant velocity, then we can use the average rotational. Just like we could use, if it's constant velocity, we could use the average velocity, we could use the average angular velocity. But if we want it for an instant in time, we would use just the instantaneous linear velocity or the instantaneous angular velocity, which of course would be equals 2 pi over t over little t, 2 pi over delta t as delta t goes to 0. Now, secondly, we can look at the units. Oh, we got to look at the units of the formula after we defined it over there. And let's now use a different color, green. The moment of inertia has units of mr squared, so that's kilogram meter squared. So kilogram meter squared, and omega is radians per second. So let's put those out here next to each other. Kilogram meter squared, radians per second. And kilogram meters per second. So let's cross off the things to see if we have the same units. Kilograms, kilograms, per second, meter, and meter squared. Meters and meters squared. So they do not have the same units. That's important for us to understand. They do not have the same units. So where we've spoken previously about the law of conservation of energy, and that energy can be made up of a whole variety of the initial energy or the total energy of the system remains constant, and the initial energy is equal to the final energy, instantaneous energy, That means the total energy is also due to all different types of energy: total mechanical and vibrational and thermal and light energy and rotational energy. We know TME is related to the translational kinetic, the gravitational potential, and the potential energy of a spring. So we have kinetic and rotational kinetic. Well, in the same sense, we have a conservation of momentum, which is P0 equals P, but we can't simply just mathematically add the linear and the rotational momentum. But the concept still holds, is that the total momentum will be equal to the linear plus the rotational. But we can't just simply mathematically add them. The idea that the total momentum is a combination of the two. So let's apply the units to the change in momentum and the change in angular momentum. We still have kilograms. And the velocity change, if we went, say, from 4 meters per second to 6 meters per second, is 2 meters per second. So the fact that it's a delta has no effect on the units. So it's still kilogram meters per second. And of course, over here, we would have the same thing: kilogram meters squared radians per second. So we end up having the same units and the same discrepancy with the units, but the units of change in momentum are the same as momentum. Well, next, let's apply this to a sample problem.